All right, Physics 12, we are starting our next unit now. We are going to be looking now at electricity and fields and electromagnetism, okay? So clearly we're in a little bit of a weird bind situation where we've got quite a bit left to cover and I've been limited to 3 weeks to try and get as much done. So you're going to get a few more video at least every other day at this point in time, and they might be a little bit longer. I'm going to be combining as much as I can in kind of like a 45-minute session, but you're just not going to get as many big assignments anymore. There'll just be a lot more little check-ins as we go, because I think it's more important that we at least cover the material, and you'll have the worksheets for practice and the solutions to kind of check on how you're doing, but just not the big assignments that are going to be kind of taking up my 3 hours a week. Instead, I want to use those 3 hours a week of material for being able to present the material so you at least have some understanding of it, okay? That being said, we're going to try and get through as much as we can with the electricity, electrostatics, circuits, electromagnetism stuff. I think we might be able to get through that completely, and it would just leave the modern physics and waves left. And what I'll do is for those who are interested, I can prepare a set of like PowerPoints and attachment videos and articles and different readings and stuff that you could potentially do on your own time if you so choose, if you feel like you want to have that to be prepared for next year, whatever you're choosing to do. But if you know you're not doing anything with physics later, then don't worry about it, okay? But that's the plan now going forward, okay? So like I said, we are starting a new unit. Today we're going to look at electrostatics, Coulomb's law, and electrostatics with multiple forces. Okay, so let's go. Okay, so we start obviously with the introduction to electrostatics. Okay, and when we talk about electrostatics, it's the study of stationary electric charges or fields as opposed to electric current. Okay, so we will be looking later at a little lesson on circuits, and then we'll be talking a little bit more with current there. But when we talk about electrostatics, we're just looking at stationary electric charges or electric fields. Okay, so when we talk about an electric force, okay, that is the attraction or repulsion of different particles and materials based on their electrical charges. Okay, so I mean, we've had, we've obviously seen a lot of forces before, right, where we can apply a force. There can be force of friction, and we've got the force of gravity that pulls something towards the center of its mass. You got centripetal force, right, something working, pulling it towards the center of a circular motion, right? But when we talk about an electrostatic force, it's that attraction or repulsion of the particles based on their electrical charges. Okay, and we should kind of have a general understanding at this point, from just earlier elementary science classes, that that charges can either be considered positive or negative, right? And you have like charges that will repel each other, and opposite charges that will attract, right? And those are the different forces that are at work within those particles. Right. We also look at the law of conservation of charge. So just like we've seen the law of conservation of momentum, we also have that law of conservation of charge, where when all the objects in a given system are being considered before and after a given process, the total amount of charge is the same before the process starts as it is after the process starts, right? So there is no, real destruction of anything again, right? It's all conserved, right? So it might mean that the individual charges on particular items will shift, but the overall charge, like the net charge of the entire system, would still be the same, right? So one item might gain electrons and the other one might lose, but ultimately you still have the same number of electrons present in the entire system, okay? All right, what you're noticing in that video, or not video, in that diagram in this particular slide is, again, just kind of showing how we're drawing these attractive forces. Okay, so again, already kind of alluding to the fact that, we know that opposite charges are going to attract, right? What you're seeing here in the convention is the charge from the positive, okay, and that is convention. So what you're seeing here is that these forces are this positive is being attracted to the negative, right, and it will kind of make these interesting fields of electrostatic force. Okay, so basic examples, like I said, you've already kind of probably been introduced to this concept before, but if we want to talk about the examples, right, that classic, prank of you rub your feet on your carpet and then you touch them, you can give them a shock, right, because you've transferred electrons, right? An excess of electrons from your body into theirs, right? Yeah, even the fact that when you bring like a neutral item close to a charged item, right, it kind of has that attraction as well, right? So for example, if you go close to a television, right, it has a charge to it, right? And if you just bring your like neutral arm hair close to it, right, that neutrality of your hair, like it actually, the particles within the hair itself will rearrange themselves to show that kind of attraction of forces, right? Lightning is your big example of an electrostatic force. We'll talk a little bit about that later. And even dryer sheets, right? So dryer sheets being placed in with a load of clothes that are drying, and you want to get them so that they won't be sticking to each other, right? So it kind of takes on that extra, those extra forces and charges so that your clothes don't get them and they don't stick to each other. All right, so again, as mentioned, we already kind of know this idea where opposite charges will attract and like charges will repel. Okay, this will come in handy when we're looking at like the net force on a particular charge. We'll get into that this lesson, right? So I mean, you know, we've seen it with magnets, and it's true as well for electrically charged particles as well, right? So again, if you hold two of the same charge close to each other, they will repel each other. They will only come so close together, right, at equilibrium, whereas if they are unlike charges, opposite charges, they will attract to each other. And like I mentioned before, your neutral charges are attracted to any object with a charge, right? So two neutral objects aren't really going to do anything. There's no attraction or repulsion there. However, if one object has a charge and the other is neutral, you will still get an attraction there. So a common example, maybe from like a junior high science class, would be taking a balloon, rubbing it against your hair, right, charging up the balloon, and then being able to stick it to a wall, right? The wall is inherently neutral, right, and you've charged that object. And when you do that, it's like the particles within the wall itself kind of rearrange themselves in a way that they're able to kind of point their positive like protons towards the end of the wall, right? And you can actually get the balloon to stick to the wall for a little bit. Okay, so again, when we're talking about these, you know, charges and stuff, we got to, you know, keep some important things in mind, right? So a negative charge is caused by an excess of electrons, and a positive charge is caused by a decrease in electrons, okay? Your protons are never moving, right? Number of protons in a substance isn't going to change, but you can transfer the electrons. I mean, you just think about that chemistry-wise, and that just makes sense, right? I mean, your protons are kind of stuck in your nucleus. You're going to need a lot more than just a, you know, rubbing of a object on the floor or on your hair to cause those protons to be released from their nucleus, right? But when it comes to electrons, right, where they're just kind of orbiting in their own kind of, you know, field themselves, they can move from one charge or one charge item to another, okay? So if, you know, the electrons go from one spot to another, right, it's giving electrons, so it's causing something to become negative, right? If it overpowers it, it's negative, whereas if you've lost your electrons, you could become positive, okay? Now, what we'll be looking at in just a slide or two is Coulomb's law, okay? And what you're going to notice is it's going to look almost identical to our formula for universal gravitation, right? So that one was, you know, our Fg is equal to our G universal gravitational constant multiplied by the mass of the two different planets, right, divided by the radius in between them squared, right? And what you're going to get is almost the exact same thing, where there's going to be a Coulomb's constant, the charge of two different particles divided by the distance between them squared, okay? But the big thing that's different here is that with electrostatic forces, they're different in that electrostatic forces can either repel or attract, okay? With our universal gravitation, right, that force of gravity is always attracting, right? You are always having the larger object pulling the smaller object into its orbit, right? With charges, again, it's going to be important to look at, well, you know, what are these two charges I'm dealing with? Are they both like charges? Would they be attracting to each other? Or would they be repelling each other? How would that work, right? So it is going to change kind of how we look at those calculations as well, okay? Just in terms of orientation, right, and then direction. So again, when we're solving for those electrostatic forces, we're not going to use positive or negative signs to indicate direction. Instead, your direction of force is based on whether there's an attraction or repulsion. Okay, so we're going to be having to closely look at the particles in question, what are their charges, would they be attracting, would they be repelling, in what directions would they be doing that, with what type of force would they be doing that, and then being able to kind of put it all together. Okay, so as mentioned, with Coulomb's law, it was in 1785 that Charles Coulomb began working with those pith balls, right? So they're like just little cloth, small balls, to try and figure out the force between them. So he could charge them and then place them at determined distances apart and see kind of what angles they would deflect, right? So you tried to put them together, and then they would move apart, and then they'd reach a state of equilibrium where they were happy enough to be far enough away from each other that they were, at equilibrium. So he was able to kind of see, okay, well, if I give these ones this charge, what happens with the distance in between them, and what angle do they deflect? Did all the research, saw, collected the data, graphed it, and then kind of said, all right, well, based on this, the force between these two charged objects is proportional to their charges, right? And it's inversely proportional to the square of the distances between them, right? Giving you the following formula. We'll kind of come back to it, right? Where it's that there's their two charges divided by the distance between them squared, right? Now, again, with any sort of proportional relationship, if you want it to turn into an equality relationship, you need a constant. So you had Newton that came up with this universal gravitational constant that worked for gravitational charges between, two large bodies, but what we have here is Coulomb's constant, okay? And now when we talk about a Coulomb, obviously named after scientist, it's a constant that's equal to the charge of 6.25 times 10 to the 18 electrons, okay? So one electron or a proton has a single charge of 1.60 times 10 to the negative 19 coulombs, right? So again, right, there's your 1 coulomb, 6.25 times 10 to the 18 electrons, and then if you wanted to do a quick calculation there to get your 1 electron, you would just take your 1 coulomb divided by that value, and you can get the charge on a single electron and charge on a single proton. Okay. Again, talking about that constant, right, in order to turn that proportional relationship into an equation that can be used universally, we have to develop some sort of constant. What is that relationship? When I do this division every time, what is the constant I get, right? Just like how every time you take the diameter of a circle and you divide it, or the circumference, and you divide it by the diameter, you get pi, right? Same kind of thing's happening here. What's the constant that we need to always use to make this work? And it's this value here of 9.0 times 10 to the power of 9 newtons times meters squared over coulomb squared. Okay, again, the units here are just coming from the fact that we needed to make everything cancel out in order to give us a force, right? So if we go back to this equation here, right, this would have been a charge measured in coulombs. This would have been a charge measured in coulombs. So our numerator here would have been coulomb squared. This would have been divided by meters squared. And we're trying to get a force, which would mean it would need to be in newtons. So we have to kind of pick, okay, well, what units would this need to be in order to get everything to cancel, right? So if we need the coulombs squared, you got to have the coulomb squared in the bottom. And if we need meters squared, we need that at the top. And then obviously we need newtons. So that's where that constant is coming from, okay? Again, did I mention all that? I think so, right? Yeah, so the charge of that 1 electron or proton, that's the element of your fundamental charge, just because it's the smallest amount of charge. Nothing smaller than a proton or electron has a definite charge. Again, a coulomb is a very, very large amount of charge, right? I mean, if we go back, it's the charge on 6.25 times 10 to the 18 electrons, okay? So oftentimes we're not dealing with that large of a charge. So really you're going to see a lot of things written in either microcoulombs or nanocoulombs or picocoulombs or femtocoulombs. So just kind of, refer back to your kind of SI units there in terms of scientific notation and what your prefixes are going to mean, right? So we'll be dealing a lot with the micro, so it's just anything you've been given, just multiply it by 10 to the minus 6, okay? If it's in micro. If it's nano, multiply it by 10 to the minus 9. Okay, so again, we're here at the formula. I've already kind of alluded to it, right? So again, this looks almost identical to our universal force of gravitation, right? Where this was like Fg is equal to the universal constant g, and then mass 1 times mass 2 divided by the radius in between them squared, right? And again, it's almost identical, okay? Where instead you've got Coulomb's constant instead of Newton's gravitational constant. You've got two charges measured in coulombs, okay? And then this would be the distance between their centers, right? And then what it gives us is the force, not force of gravity, but the electrostatic force between the charges, right? So you'll see that oftentimes as FQ, right? So not FG, not gravitational force between the objects, but FQ, right? The electrostatic force between the objects. Okay, so let's finally kind of get to a problem where we might use this formula here, okay? So if we have a small sphere that's carrying a charge of minus 8.0 microcoulombs, exerts an attractive force of 0.5 newtons on another sphere carrying a charge with a magnitude of 5.0 microcoulombs, what is the sign on the second charge? Okay, well, that one we don't even really need to do much work. We just talk about the fact, well, reading that question, our first sphere has a charge of negative, right? So it's a negative charge. It's saying it exerts an attractive force, which means knowing that opposite charges attract, right? While we don't know the sign of this charge, we know that it's being attracted to this, so this would have to be positive, right? So our sign would just be positive, just based on the way that that question is worded and knowing that the first charge is negative and it's been an attractive force, okay? So the sign of our second charge is just going to be positive. Now we get into, using the formula, where it's what's the distance of separation of the centers of their spheres. So now we will take a look at that, okay? So, board, okay? So what you've got is, we can call this Q1, right? And we know that Q1 was given a charge of negative 8 microcoulombs. We know that there's a second charge, Q2. We know that its magnitude is that it was 5 microcoulombs. All right. That was there. We do know that that's positive now just because it was an attractive force, okay? We also have that the attractive force was 0.50 newtons, and we've been asked for what's the distance between their centers, right? What's the radius, okay? Now, when we use this formula, we're not going to be putting the positive and negative signs of their charges in the formula. Okay, we're just going to be using the magnitudes there, right? The positives and the negatives really only just come down to talking about whether or not they're going to be repelling or attracting each other. Okay, so when we go to plug that in with our formula, and we see, okay, using our Coulomb's law, right? So FQ is equal to K, Q1, Q2 over R squared, right? We start putting in these values. Now what we're trying to solve for here is R squared, right? So if we do a little bit of rearranging here, right? So you can divide by the constant, right? So what we can get is FQ over K is equal to Q1, Q2 over R squared. I can then cross multiply and get FQ R squared is equal to K Q1, Q2, and then get that R squared is equal to K Q1, Q2 all over FQ, and then it would just be a matter of square rooting that. Okay, so I'm just going to use that, okay, and plug in the values and go. Okay, so where is my whiteboard eraser? There it is. All right, so if we do that, right, using that rearrangement of our formula, okay, we can, well, even just square rooting it after the fact, right, we can get that R is going to equal the square root of, so K was our Coulomb's constant, which is our 9.0 times 10 to the power of 9, and then that's newtons meters squared per Coulomb squared, right? And then we're multiplying by our two charges. One at, the first one was 8 microcoulombs, so that would be 8 times 0 times 10 to the minus 6 coulombs, okay? And then multiplied by the other one, which was at 5, so 5.0 times 10 to the minus 6 coulombs as well. And that's all being divided by that force of 0.50 newtons. Okay, so again, what you'll notice here, even just with your unit analysis, right? Coulomb squared will cancel with your coulombs here, right? Newtons will cancel here, and you'll just be left with meters squared, which then you're square rooting, leaving you with meters. Okay, so again, very, very carefully plugging all of that into a calculator, right? Step at a time, or lots and lots of brackets. And ultimately what you get when you do that is a value of 0.84853 meters, or since in this question we're only ever really given two sig figs, we can say that the distance between their centers is 0.85 meters, or if you'd like, just 85 centimeters. Okay, so there's your, basic use of Coulomb's law, where you can rearrange that to solve the distance between things, or the attractive force, or even the repelling force between two different objects. Again, depending on what the situation calls for. Okay, so again, there's that solution, and there's a few practice problems from your textbook, just kind of using Coulomb's law and identifying whether forces are attractive forces or repelling forces. Okay. Within this video, I am going to combine now how we deal with electrostatics with multiple forces. Okay, what if it's more than just two objects? What if they're not just in a straight line? How do we deal with all of that, right? And that's where all of our work that we've been doing with dynamics and dealing with net forces and adding vectors and subtracting vectors and all that kind of stuff is still going to come into play. Okay, so we're going to add that to our lesson today. Okay, so we'll deal with multiple charges today as well. Right, so again, all of our forces, including our electrostatic forces, they are still vector quantities. So that means if we are dealing with multiple forces that need to be added, they need to fall under the same category of vector addition. Okay, so that would mean using your tip to tail method and looking at, okay, well, what's my overall force here? Okay. Again, remember that our equation with Coulomb's law used only those scalar quantities, with the understanding that the direction of the force always lies along the line joining the center of the two charges, and those forces could either be attractive forces, right, where it's being drawn towards another object, or it's being repelled away from another object, right? So it could be, you've really got to look at what are those charges, what are the sign on those charges, to get an idea of what direction is the force, the net force being applied. Okay, so like I said, when one charge experiences a force from more than one other charge, we have to resolve that direction by using vector addition. Okay, so when we're looking at these types of problems, right? So you might be asked for this force acting on one particular object, right? So look at that one particular charge or charged object. Find what are the forces, what are all of the forces acting upon that particular object, okay? Remember that if our signs for relevant forces are the same, it would indicate repulsion, right? So it would mean it would be pushed away from that other one. If the signs are different, it would mean attraction, right? So then that indicates that the direction for each arrow is going to create that right triangle, okay? And what you're going to get is that combination of multiple forces being put into your right triangle using your tip to tail method. Use your Pythagorean theorem to get your magnitude, and then of course using tan theta, or like tan inverse, to find your angle. And you can talk about clockwise or counterclockwise when indicating direction, like clockwise from the positive x-axis or counterclockwise from the positive x-axis. Worst comes to worst, you can always just go back to your north, south, east, west. That can work for conventions there as well, because it's standard in terms of how you would sketch things. Okay, so let's just kind of go straight to the sample problems here, because this is where it'll make a lot more sense. Okay, so in this first one, what you've got are three charges, A, B, and C, right, with the given charges of positive 5 microcoulombs, negative 2 microcoulombs, and positive 3 microcoulombs, right, and they're arranged at the corners of a right triangle as shown, and we're being asked for what is the net force on charge C. Okay, so I'm just going to redraw that on my own board. Okay, so we've got A, and that's plus 5. We've got B, at -2, and we've got C at +3, and 2 centimeters along the bottom, and 5 centimeters along the top. Okay, so we're being asked specifically, what is the net force on charge C? Where is my video? Here it is. Okay, so you've got 2 different objects acting on C here, okay? So with charge A, okay, you'll notice that these are the same, right? They're both positive charges, okay? So this would be a repelling force. So C is going to try and move away from A, right? So if this is C, right, we're just thinking about C on its own, right? You're going to have the force between A and C acting in this direction. Okay, the electrostatic force connecting A and C is going to be pulling it down because C is trying to get away from A due to there being the same charges. Okay, with charge B, right, this would be applying a force as well. Because these are opposite charges and opposites attract, C is going to be trying to go in this direction and moving towards B. So at the same time, it's trying to move away from A, but towards B. Okay, so it's moving down, and it's also moving to the right. Right, and that's the electrostatic force from B to C. Okay, so these are the 2 forces that are acting on C right now. We're going to need to figure out their magnitudes, and once we do that, we know that its net force can kind of be drawn like that, right? Or if we wanted to do tip to tail, we can say, okay, well, it's going to be acted on, it's going to be moving this way, and it's also going to be moving down, and this is our overall net force that's happening here. Okay, where this would be our force of A to C that's pulling it down, our force from B to C pulling it to the right, right? And then we would need to figure out, okay, well, what is this value, right? Using Pythagorean theorem there, as well as what is this angle, okay? All right, so, you know, that's all well and good, but we actually need values here, okay? So how do we actually figure out the forces for A to C and for B to C? Okay, we can disregard A to B, right? That's not a force acting on C whatsoever, right? The question we were asked is what's the net force acting on particle C? And this force that's connecting A to B has no bearing on C whatsoever. Okay, so we disregard that, and we're just looking at these 2. So this is, again, where we can use Coulomb's law. So if we look at the force for A to C, right, we can use Coulomb's law in that same way. We can say, all right, well, I've got my constant, which was my 9.0 times 10 to the power of 9. I'm going to skip the units only because it's so hard to try and fit it all on this tiny whiteboard. Okay, multiplied by our 2 charges, right, and we just include the magnitudes there. So it'll be the 5 microcoulombs, so times 10 to the -6, multiplied by the 3 microcoulombs, and then that's all going to get divided by the radius in between them, which in this case is 5 centimeters, but that has to be put into meters for this formula, so 0.05, and then squared. Okay, so again, very, very carefully go through that. It should look more like a 3. Right, so multiply all that through, and what you get there is a value of 54.0 newtons, okay? And like I said, that's a repelling force, so it's pulling down on C here, okay? We then do the same thing, right? And we do the calculations, but for B to C, like this. Okay, so constant still stays the same. That's still the force for C. We change our force, charge for C is the same. We change our charge for C. Again, B, so we're using only the scalar part of it, right, the magnitude, so that's the 2. And now the distance in between them is 2 centimeters. So again, it has to be in meters, but I can change that there. Okay, so again, you're able to use Coulomb's law, right, the constant, multiplied by the charges of the 2 particles, right, just the magnitudes, divided by the distance between them squared. Very carefully plugging all of that in, and you get a value of 135 newtons there. Okay, so those are our 2 forces. So now that we're able to kind of resolve those, just to kind of show that triangle a little bit better is, again, knowing that on C, right, it's trying to pull away from A at 54 newtons in that direction. It's trying to move towards B at 135 newtons, right? And if we kind of combine those with tip to tail, right, here is our resultant, right, or our net force on C, right? And we can solve for that just using Pythagorean theorem, right? So our net force on C is going to be the square root of 54 newtons squared plus 135 newtons squared, and then square root that, which gives us a value there of 145.4 newtons. Okay, and then the direction, right, is going to be found using that angle. Okay, so I can go theta is going to equal tan inverse of 54 divided by 135. Okay, and we get an angle there of 21.8 degrees. Okay, so now if we're going to kind of go back with sig figs here, you know, in our main problem we really only had 2. So this I would round to 150. So our answer would be 1.5 times 10 squared newtons. I'll just round that to 22 degrees, right? And it'll be 22 degrees clockwise from the positive x-axis, right? So 1.5 times 10 squared newtons, 22 degrees clockwise from positive x-axis. Right, and that would be our final answer there in terms of the net force acting on C. Okay, and again, you could do this acting on any of the particular charges there, right, on A or on B. Okay, so again, there's that solution, right? We've just said clockwise from the horizontal there. Go from there. All right, let's do this one as well. So here you've got two 2.6 gram balls are attached to each other on the end of a string that measures 1.8 meters. Okay, so this is one entire string here with a length of 1.8 meters. The balls are given identical charges, so the charge of Q1 and Q2 are identical. And the midpoint of the thread is then suspended vertically, right? So it's like you found the exact midpoint, put it up here, right, attached it. So if we know that this whole length of the string is 1.8 meters, just this value of L is going to be 0.9 meters. Okay, they're left to drop, and then what ends up happening is because they were given identical charges, meaning they would repel each other. Okay, they've, instead of just falling straight down next to each other, they've now pulled themselves apart. Okay, and they rest in equilibrium. Okay, and when they're at equilibrium, their centers are 18 centimeters apart. What is the magnitude of the charge of each sphere? Okay, we don't know whether they're both positive or negative. It wouldn't really matter, okay, because it would just be repelling anyway, but we're just being asked what's that magnitude. Okay, so let's work through trying to figure this one out. All right, again, I'm just going to kind of redraw that diagram on my board. So we've got Q1 here. Got Q2 here, L, X, and theta. Okay, we know that that distance is 18 centimeters apart here. Okay, so going to this, okay, so we knew that these were attached to a string that was 1.8 meters long, and then it was just attached up here. Okay, so in saying that, we know now that this is going to be 0.9, right? 1.8 meters divided by 2 is 0.9 meters lengths here. Okay, because it said it was the midpoint that was hung up there. Okay, we know that Q1 and Q2 are identical, right? So when it comes to our formula, we know that that value is going to be the same, right? So it's essentially just the same charge squared, right? We have that the radius, right, the distance between the two is 18 centimeters, or if we have to put it in meters, 0.018 meters. Just double checking that. Yeah. Okay. No, that's not true. It's 0.18 because it's not. There we go. Okay. So we've got that as well. Now, if we were to try and look at, Coulomb's law here, right, we can say that, okay, well, the electrostatic force is going to equal K, Q1, Q2 over R squared, right? K is a constant we know. These two values we know are the same, right? So it's really not two different variables, it's just the one. So you've got this equilibrium force, or the electrostatic force, sorry, is going to equal to that 9.0 times 10 to the 9, right? Multiplied by, let's just call it Q at this point, right? Q squared over 0.18 squared, right? You could do this math here and get that the electrostatic force, oh, bless me, is going to end up equaling 2.78 times 10 to the 11 times Q squared, right? Which is all well and good if we know what this force is, okay? Now, we have to now apply a little bit of something else, because what other forces are acting here are the force of gravity, right? These things are being just suspended. So if we kind of took out the electrostatic force part, right, and we just thought, okay, well, what would have been the force of gravity just pulling it down here, right? Like when this was first put down, it would have been coming straight down, right? So you would have had this kind of force of gravity here, and then you've got your electrostatic force pulling in that direction as well, right? So we can actually figure out, okay, well, what is our force of gravity? Well, that's just mass times acceleration, right? Or in this case, gravitation on Earth, right? So Fg, the mass of that ball, was 2.6 grams, so 0.0026 kilograms. That's why I was getting messed up with all my zeros. Right, multiplied by our 9.81 meters per second squared. Okay, so our force of gravity here will end up being 0.025506 newtons. Okay, so that's the force of gravity pulling straight down. Okay, but remember that we have this electrostatic force, right, that's happening in between them, right? So what we then need to figure out is, okay, well then what's just this value here, right? So what we can do there is, if this is a force here, and this is our electrostatic force here, right, pulling in between these two things, right, pulling in this direction, right, we can solve for this just using right angle trig, because we now have a value of the force pulling straight down, so that's 0.025506 newtons. We can actually figure out this particular angle, right, going back to just a basic triangle here, where we knew that this was 0.9 meters, right, and then this distance in between the centers was 18 centimeters, so just cut that in half, and you get a value of 0.09 meters, right? So it would have been 9 centimeters hanging this way, right? And we knew that was the same based on, it's resting in equilibrium, it's cut in half, okay? So we can figure out what theta is using a nice little sine inverse, right? So theta here, right, because this is the opposite side, this is the hypotenuse side, so we can say, okay, well, theta is going to equal sine inverse, there's not enough space on this board. Okay, so that's 0.09 meters. So our theta is going to equal sine inverse of opposite over hypotenuse, 0.09 meters over the 0.9 meters. And theta ends up equaling 6.4 degrees. Okay, so if theta is now 6.4 degrees, and now we look at things in terms of forces, right, then that means that FQ, right, the electrostatic force, right, pulling on one of the charged particles going this way, right, is going to end up being, it's the opposite of that angle, and we have FG, which is the adjacent, right, so what we can set up then is this idea of, okay, well, tan of 6.4 degrees is equal to FQ divided by adjacent, which is FG. We have FG over here, right, our 0.025506 newtons, which can get plugged in here. So our FQ ends up just being tan of 6.4 degrees multiplied by FG, right, which is this value here. And when we go to calculate that, we end up getting a value here of 2.57 times 10 to the minus 3 newtons as our value of FQ. Okay? And then that goes back to that original equation that we set up, right, where we had said that, oh, FQ is equal to that K, and then Q1 times Q2, but they were the same, right? And we rearranged that and did what we could and said, okay, well, FQ is going to end up equaling that value of 2.78 times 10 to the 11, and that value of Q squared. We said, well, that was all well and good if we knew FQ. Now we do know the electrostatic force, right, pulling to the other side there, so we can fill that in, right? And now this becomes 2.57 times 10 to the minus 3 newtons is equal to that 2.78 times 10 to the 11 times Q squared. And now we just need to divide both sides. So we get this 2.57 times 10 to the minus 3 divided by 2.78 times 10 to the 11 is equal to Q squared. So that gives us 9.255 times 10 to the minus 15 is equal to Q squared. And then we would just square root that, and you get a value of 9.62 times 10 to the negative 8 coulombs is equal to the charge on each. Huh. All right, it's a process, but it works. Okay, so again, it's still thinking about, okay, well, what other forces are acting on this? And if something's just hanging, well, you've got force of gravity that would have been pulling straight down, and the electrostatic force is what's pulling it to the side, right, away from that repulsion, away from that other charged particle or other charged ball, right? So then you can kind of just, use your trig to figure out, well, what is that kind of, what's that angle, and what's that force going to be, right? And then kind of set those equations equal to each other. Okay, where are we at now, right? So again, I guess I missed my rounding. It should just put in 9.6, not 9.62. Okay, so we've got one more problem to look at here, right? And then I'll be done. So in this one, you've got a right triangle shown below, has each of the following charges placed on each of the letters indicated. Okay, so again, we've got charges being placed in a right triangle, charges A, B, and C. Okay, you've got the charge on A is 4 microcoulombs, the charge on B is negative 5 microcoulombs, and the charge on C is 7 microcoulombs, and we're trying to determine the net force acting on point A. Okay, so again, what we've got, if I redraw that right triangle, okay, got A, B, and C. The distance between A and B is that 3.5 meters. The distance between B and C is 2.7 meters, and we have this angle there in between. Okay, so if we are going to look at net force on point A, right, just by listing those charges again, right, so charge on A was a positive 4 microcoulombs, charge on B was the negative 5 microcoulombs, and the charge on C was the positive 7 microcoulombs. Okay, so just kind of thinking about net charge on A right now, right? I know that A is positively charged, B is negatively charged, and C is positively charged here as well. Okay, so what we kind of need to look at is, in general, what forces are going to be acting on A. Okay, well, A is going to have a force coming from B, right? So A, if we think about A here, it's going to be attracted to B, so it's going to be pulled in that downward direction. Okay, so that's going to be the force AB, right? It's going to be pulling on A straight down to B. Okay, but you're also going to have a repelling force, since these are both the same charges, on C, where it's going to be wanting to go in the exact opposite direction, right? This way. Okay, at the same angle. Right? So once again, I need to try and figure out, okay, well, what's the sum of all of those forces? What's the total of that? And that's going to end up having to involve, again, vector components, right? Because this is now happening at an angle. So the first thing I need to do is figure out, well, what's that angle? Okay, well, that angle is relatively easy to find, okay, just by, doing some basic trig. Tan, okay, so theta is going to equal tan inverse of 3.5 divided by 2.7. And for some reason I didn't write that down. Yeah, 58.2 degrees. Okay, so we have that. So we're going to need to use that when it comes to our force for A to C. So why don't we just kind of keep going with that one for right now, because this one's going to be fairly straightforward. Okay, so if we're just kind of focusing on that force connecting A to C right now, okay, we can figure out the total force, right, just using Coulomb's law. That's going to be your K, QA, right, charge on A, charge on C, divided by the distance between them squared. Okay, again, you have a value of K, that's the constant of 9.0 times 10 to the 9. Okay, we have our relative charges. They are 4 microcoulombs and 7 microcoulombs. Right, so it's your 4.0 times 10 to the minus 6 and your 7.0 times 10 to the minus 6, all divided by, now the distance between them, we would also need to find using Pythagorean theorem, right? So you'd have to do 3.5 squared plus 2.7 squared, then square root it, and get this value. But just keep in mind, once you get that value, you're going to square it again anyway, right, in your equation for r squared. So if you just take each of these and square them, and then add them, right, so go 3.5 squared plus 2.7 squared, you just get 19.54. If you were to square root it, that gives you the side length, but you're just going to square it again anyway and give you the 19.54. Okay, so that's the value that's going in there, and that's already been squared. Okay, so all of that you can figure out, plug that all in, you get a force FAC of 0.0129 newtons. Okay, and that's exactly in that direction, right? Pulling that way. Okay, but again, we're trying to find net force. So I'm trying to figure out, okay, if that's the force in that direction, right, at 58.2 degrees, right, north, or, west, 58.2 degrees north, okay, what is it just in terms of x and y components? Okay, so in just kind of thinking about that here, okay, I can figure out, okay, well, the x component is going to be along this side, and the y component is going to be up this way. So what you'll just do is basic trig again, right? So what you end up having, if I erase this main triangle now, and just think about that force, right? That's that electrostatic force from A to C pulling in that direction, right? And that being 58.2 degrees, right? This is F of C in the x, and this is F of C in the y. And they can just be used by using basic trig there. Okay, so in that sense, this is just going to be F of AC times cosine of 58.2 degrees, right? So our F of AC in the X is going to be that value of the 0.0129 newtons multiplied by the cosine of 58.2 degrees. Okay, and that ends up giving us a value of 7.87 times 10 to the minus 3, okay, and it's pulling in that direction, okay, negative x direction, right? Then if we're trying to find FAC in the y, okay, it's that same value of that 0.0129 newtons multiplied by the sine of 58.2 degrees, and then that value gives you 0.0102 newtons, right, pulling up, okay? So we kind of keep those in our back pocket, right? Then we have to look at that other force, F of AB, that's pulling straight down on particle A, okay? Now that one's a little bit easier because it's just straight down. It's only in the y component. We don't have to deal with any sort of angles. It's just figuring out what that value is, right? So using Coulomb's law, value of K, the constant, 9.0 times 10 to the 9, multiplied by the magnitude of the charges, which in this case is A and B, so 4 microcoulombs times 5 microcoulombs, so 4.0 times 10 to the minus 6 times 5.0 times 10 to the minus 6, all divided by the distance between them, and I erased it, of course, but it was 2.7, no, it wasn't. It was 3.5 meters, right, because it was the one going down, 3.5 meters squared. And you can calculate all that and get a value for F of AB to this distance of 0.01469 newtons. Okay, so here are your key things here, right? So this force is pulling it this way, right, to the left. This force is pulling it up, and this force is pulling it down. Okay, so the sum of the components in the X is just this, right? So if we think of this, kind of this diagram, I'm going to redraw it, right? Just the things pulling on A, right? In the X, all we have is this 7.87 times 10 to the minus 3 newtons, right? In B, in the vertical component, you've got one force here pulling down, the force of 0.01469 newtons, but then this force is pulling up at a value of 0.0102 newtons, right? So we can add these together quite easily, right? And then quickly realize, okay, well, if I take that and essentially just subtract that, right, what I end up getting is the following diagram, right, where from point A, you still have this value of 7.87 times 10 to the minus 3 newtons pulling in that direction, but overall, vertically, you're being pulled down by a value of 4.47 times 10 to the minus 3 newtons being pulled down, right? And all I did there was I took that 0.01469 and I subtracted 0.0102, okay? I think we get 4.49. I must have used more decimal places when I did this, okay? But that same idea, okay? And then you can kind of add those together, right? Now your net force is doing this, right? If we add them tip to tail, and we go that way and then this way, again, this is our F net. We solve for that using Pythagorean theorem. Clear the board once again. Right, so our F net on A here is these two values squared and then added and square rooted, right? Give myself even more space. So the square root of this 7.87 times 10 to the minus 3 squared plus this 4.47 times 10 to the minus 3 squared, right? Add them, square root them, you get F net as being a value of 9.1 times 10 to the minus 3 newtons, okay? That's what we end up getting, and that's me already kind of putting in the sig figs correctly. I think you end up getting something more like 9.055, right? But let's call it 9.1 for our 2 sig figs. And then we just need this angle here, okay? And then once again, what you have is the opposite and the adjacent sides. So your angle is going to be tan inverse of that 4.47 times 10 to the minus 3 divided by 7.87 times 10 to the minus 3, and that gives you a value of 33 degrees, right? And we would describe that as either, yes, you could call it west 33 degrees south, or you could call it 33 degrees counterclockwise from the x-axis, right? From the negative x-axis, okay? So how you want to say that is kind of up to you, right? So a lot of people just like to stick with their north, south, east, west, right? And say, okay, well, it's west 33 degrees south, right? But you could also say it's 33 degrees below the x-axis, the negative x-axis line, okay? All right, I know that was long, but like I said, I'm just trying to combine as much as I can in terms of lessons, right? It's not big worksheets, it's just kind of a few questions on both, like with the multiple charges and the basic charges. If you feel like you're okay with the basic, skip the basic and just do the multiple charges, right? I'm kind of having to leave this a little bit to you in terms of prioritizing what you feel you need to practice on, okay? And I'm just really trying to get through the material as much as I can, okay? So good luck. Email me with any questions, but I'll have the solutions posted again as well.